Okay, guys, when the baby is in mom's womb, what happens, it's not going to have any problem with the PKU, even if he has a genetic defect and the genetic problem, but that's not going to happen. That means PKU or phenylketonuria is not going to show itself when the baby is in mom's womb. Why does that happen? Why actually when the baby is inside the uterus and in amniotic fluid, why actually this thing doesn't happen? And in order to understand it, we have to understand the anatomy of the heart a little bit. Okay, we're going to come back to this presentation. If you look at the regular circulation of the heart, this is how it happened. The regular circulation of the blood, we have two what I call the veins that are very important. That's the inferior vena cava and superior vena cava. These two actually, they're going to get the deoxygenated blood, and they're going to bring it where? To the right atrium. So all the deoxygenated blood that has been used and has gone to the cells, now it comes over here, it comes to the right atrium, and from the right atrium through the tricuspid valve, it goes to the right ventricle, this area, and from the right ventricle is just going to get pushed into the pulmonary trunk, and the pulmonary trunk is going to get branched to the pulmonary arteries, and it's going to take this blood all the way down into the lung, and in the lung, in the area that the capillaries and alveoli, they collide, it's going to make it oxygenated, and the oxygenated blood from the left side, from this area, is going to go back by the pulmonary veins. This is one of the amazing things, because here, the veins, they're going to bring the oxygenated blood inside the heart. And this is what specifically you have to mention pulmonary vein. So the pulmonary veins, they're going to bring the oxygenated blood from the left atrium, and through the mitral valve, they're going to send it to the left ventricle, and from the left ventricle, they're going to send it to by the very actually strong push, and that's one of the reasons that the apex of the heart on the left ventricle is a little bit thicker, because it's near the strong push. It's going to push the blood into the aorta, and from the aorta, the blood is going to go all around the body. This is a normal human being that has been born as a baby. It's been born, it has come to the world, or even regular person as an adult. Okay, this is how it works. But this is not exactly what happened in a baby. In a baby, it's going to be a totally different story. So what happened in a baby, because the baby is not going to be able to use the lungs, because the lungs, they are filled with the amniotic. So how the baby, they get the oxygenated blood and all these kind of stuff that it needs, like a nutrient. So what happened here, if we draw the heart, sorry, my drawing is not really good. I'm trying to make sure to make you guys understand what's going on. I'm just going to make a very simple drawing. Okay, you guys imagine here is the right atrium. Okay, right atrium. Let me just change the color. Okay, left atrium. This is the left ventricle, and this is the right ventricle, and we have to make sure to put this one here. There, you're going to divide the heart. Okay, I'm sorry. This is the right ventricle. Okay, as far as I told you, in the regular person, the blood is going to come over here, which is not oxygenated, but in the baby, everything is going to be different. That means in the baby, we need to bypass the, that part of circulation, that this blood, it goes to the lung, because there is no actual lung there. There is a lung, but it's full of amniotic, so it's not going to be able to actually to work. So what happens in this case, we have something here. There's a little hole in this area in the baby inside the uterus, and that hole is called foramen ovale. And what happened in this case, because the baby has a small hole between the right atrium and the left atrium called foramen ovale, which is right here. This foramen ovale, what it does, instead of that the oxygenated blood that was coming actually going to the right atrium and then going to the right ventricle, and from the right ventricle to the lung, and the lung from the lung actually coming oxygenated from the left atrium to the left ventricle and then going to the aorta. No, this thing is not gonna happen. Instead of that, what happens in a baby, which is very important to understand this when it's inside the womb, is like from the placenta of the mom. If we imagine this is the placenta, so from the placenta, oxygenated blood, which is full of nutrients and full of oxygen and all the amino acids and whatever we need to break down the phenylalanine, and whatever we need to break down the phenylalanine, it's in the mom's blood, and it comes from the placenta, from the right atrium, and this time it doesn't go to the right ventricle. It goes directly through the foramen ovale because there's a hole over here, and it goes directly to the left atrium. From the left atrium through the mitral valve, it goes to the left ventricle, and from the left ventricle it's going to go to aorta, and it's going to get all around the body. That's why the baby that even it has a PKU problem, it's not going to show when the baby is inside the mom's womb, because what happens, the oxygenated blood that's full of amino acids and also the enzyme that needs to break down the phenylalanine, it comes from the placenta of the mom, and it doesn't need to do anything else. It just go to the right atrium, through the foramen ovale, to the left atrium, to the left ventricle, and then go throughout the other side of the body. And when the baby is born, what happens actually, due to the pressure of the air, this is what we call physiology, physics of the body. Due to the pressure that it comes from the outside, the air pressure, what happens, the air is going to push down the amniotic into the alveoli, so it start actually opening up that space. And then the air is going to go through the pulmonary trunk and comes right behind this foramen ovale and is going to snap it forever. And this thing is going to get a snap forever. That's why the baby, when it's born, is going to have the regular circulation of the heart. It's going to go through the inferior vena cava, deoxygenated, and make it oxygenated. And that's a time that's a baby that is actually being diagnosed by the PKU, we have to be careful with, because in that moment, there is no placenta anymore, and the baby's body actually is trying to make the phenylalanine when it comes from the source from the outside. And the first bite and the first grab of the milk and the protein that is going there actually is to start producing the phenylalanine, and the danger started down there. So it's very important to find out about if the baby has a PKU in order to actually start the treatment and put him in a diet that doesn't have that much protein on it in order to actually prevent that problem. Later on, this foramen ovale is going to convert to something called septum secundum, and septum secundum is going to be a very thick muscle that is going to cover that area forever, and the person is going to have a good life. If actually the baby is born with the problem and this thing, the foramen ovale doesn't snap, God forbidden, what happens, the baby is going to have some problem, and they have to put the shunt into the baby and try to close it down if they can recognize it and diagnose it fast, because otherwise it's going to have like some brain damages because due to the not a regulated circulation of the blood. Okay, we are done. And also I forgot something about the methionine to explain it to you about the methionine. Now, methionine, what I actually forgot about to tell you, methionine also is a precursor, and it's been used in a process and a pathway of the gluconeogenesis. And what this is very important, because actually methionine is going to make the succinyl-CoA, and the succinyl-CoA, what happened actually is go through the gluconeogenesis, and it's going to get converted to the glucose in order to going back inside the blood. And most of it is going to be controlled by the insulin, because what it happens, and most of this process of the gluconeogenesis, that means making a sugar or glucose out of something which is not carbohydrate. This is the main purpose of the gluconeogenesis. For the moment that the carbohydrate intake is going low and the carbohydrates level in the blood, it's going down, and the glucose level it's going down. That's why the gluconeogenesis is going to help us in this process. And the methionine, it's actually going to make the first ingredient that we needed for gluconeogenesis, which is succinyl-CoA. So that's why it was another important thing about the methionine that we needed to know. Okay, another thing about the phenylalanine that we have to talk about it, if we go back to the presentation, and it's very important to understand it, it's the process of the making the other important, very important neurotransmitters and chemicals in our brain. So one of them is tyrosine. So phenylalanine, it's actually a precursor for the tyrosine as well. And the tyrosine is actually the next amino acid that we're going to talk about. And it's so funny because it's very easy to draw that. Let's actually first draw the tyrosine and then come back to the talking about how the uracil is going to work with that process. Okay, we're going to come back here to the whiteboard. All right. Okay. One of the reasons that I want to talk about the tyrosine right now before we actually finish the phenylalanine is because tyrosine is actually comes from the phenylalanine, and it's very easy to draw that. So if you remember, that's how we draw the phenylalanine. Okay. NH2. And here we're going to connect that phenyl group. All right. That was actually phenylalanine. And very easy to draw that as far as we see that, because it was the phenyl connecting to the alanine. Here, the only difference between the tyrosine and the phenylalanine is an OH group that comes over here, the hydroxyl group. So when you hydroxylase the amino acid phenylalanine, you're going to be able actually to make the tyrosine out of it. And this is the structure of the tyrosine. This is an aromatic amino acid, but phenylalanine was non-polar, but this one is actually polar due to this hydroxyl group. Okay, this is very important to understand the difference of this one with the phenylalanine. And then we're going to go back to the presentation, and we're going to talk about this beautiful biosynthesis pathway, which is very charming and very important. Okay, here it is. This is how actually phenylalanine is going to convert to the tyrosine, and from here that we're going to understand how the tyrosine it's going to make important chemicals and the neurotransmitters in our brains called dopamine, norepinephrine, and epinephrine, which they are so important in pleasure, in fight or flight, and a lot of different kind of stuff that I'm going to explain it to you in a little bit. So this is actually catecholamine neurotransmitter biosynthesis pathway. What are the catecholamine? Catecholamine are dopamine, norepinephrine, and epinephrine. So what happens, it's very easy to understand this pathway if you just pay attention to it. Over here we have the tyrosine. And then if you see it in this way, because they put it in the Zoeter ion, actually, Zoeter ion kind of drawing, that's why we see it like a positive and negative right here. They are charged because we know that in nature, actually, they are like this because they are ready to bind. Okay, if we pay attention over here, we're going to see the tyrosine hydroxylase. We said ase in Latin, and in the medical field, that means it's adding something. And it's an enzyme, okay? Tyrosine hydroxylase. that means what it does, it's going to add another hydroxyl group to the tyrosine. And this is right here, because this one is a part of the tyrosine, and this part, it's not. This is the new one due to this tyrosine hydroxylase, okay, in actually presence of the oxygen. Then by the DOPA, we're going to create something called DOPA, or dihydroxyphenylalanine. You see that right now? Basically, we are talking again, going back to the phenylalanine. What we do, we are just adding two dihydroxy, 1 and 2, dihydroxyphenylalanine, and this is the phenylalanine right here. You see, this area is phenylalanine. Let me just draw it like this. This is the phenylalanine, and these are the two that call it dihydroxy, okay? And then by the DOPA decarboxylase. So this molecule right now, it makes it easy. We call it DOPA. And now what we're going to do, we're going to DOPA decarboxylase. If it was saying carboxylase, that means they were adding a carboxyl group to it. But when it says DOPA decarboxylase, that means we are grabbing, in the presence of the CO2, what we are doing, we are grabbing this DOPA molecule and we are taking off this carboxyl group that it was right here. So we are taking the carboxyl group, and all of a sudden when the carboxyl group is gone, another hydrogen is going to get attached to it. So here we have the dopamine. You see that? From the phenylalanine, we got to the tyrosine, and the tyrosine to the dihydroxyphenylalanine, and right now we have one of the most important molecule in our body. And if we want to talk about the dopamine, I'm going to tell you, this is the chemical is going to give you all the pleasure of the world. When you drink, the first thing that happens, dopaminergic rewarded pathway. That's a pathway in the brain that actually it's going to give you that pleasure. When you go to the first 2 shots of your drink, you start like having, if you are 21 years old and older, what happens to you in your brain, there's a pathway, we call it dopaminergic rewarded pathway, that it's in temporal lobe and also in frontal lobe. What happened, that's in this case, all the dopamine start oozing and secreting all throughout the brain, and that's why it gives it the pleasure. And this is the main reason that the people, they drink, even when the people, they have sex, at the time that they are enjoying so much of it, because the dopamine in the brain is actually getting reproduced. When you're eating a very actually delicious steak or something, the food that you love it, and you say, wow, that's so delicious, that's a moment that the dopamine is actually working in the brain. That's why it gives you euphoria when you're drinking, or getting so actually calm, you're down to earth, you're just like very saying the stuff that tomorrow you're going to forget about it. That's actually due to the dopamine. But there's a problem with drinking too much. What happens, remember, we study about the gamma aminobutyric acid, that at the end of the the slide, I'm going to talk about it, and at the end of the video I'm going to explain it to you. What happens, that's a moment that the alcohol start affecting the GABA, which is gamma aminobutyric acid. And the gamma aminobutyric acid, I told you, is a regulatory neurotransmitter between the synaptic cleft area. What happens when the signal is going, it's going to regulate it and slow it down. But when the alcohol goes there, it's going to slow it 100 times more. That's why the signals all the way, they're going to get faded. And mostly nothing from the short-term memory is going to get to the hippocampus area, which is a long-term memory, and the person is going to have a blackout. And when you give something to the body, which comes actually, the body has it endogenously, and you give it exogenously to the body, what happens, the body stop or reduce the production of the chemical that it was actually already reproducing. That's why when you give too much alcohol to the body stop producing GABA, because it says there's something coming out from the outside that is doing the same thing that actually GABA is doing. So why should I actually produce something like that in order to do that? So because the body wants to keep you in the homeostasis level. And that's why we see the people that are getting alcoholic, all of a sudden, due not to receiving the alcohol, they're going to go through the seizure in the middle of the street. And the reason is because they don't have enough GABA to regulate the signal, and there is no alcohol to regulate the signals either. So that person is going to go through the seizure. Okay, that makes like a dopamine a very important, actually. Let's go back to the dopamine. That's what actually makes the dopamine a very important substance and very important chemical in our brain. Then, due to the dopamine beta hydroxylase. So, in presence of the oxygen, dopamine beta hydroxylase, that means what it does, again, it's going to add the hydroxyl group. Don't let that beta things actually confuse you. Beta mostly is a beta carbon. So dopamine beta right here on this carbon, that's a beta carbon. What it happens, because this is the alpha carbon connected to this amine, and we have the beta carbon over here. So on the beta, we are adding another OH group. And here we have the what it calls. So we're gonna create another molecule which is called norepinephrine, which is very important, especially when we are talking about the pharmacology in the future. When we talk about the SSNRI medication, this N actually goes back over here to the norepinephrine, and what it does, because we told you that selective serotonin SSRIs, they can actually, like one of the example was the Celexa, and another example was Lexapro, selective serotonin reuptake inhibitor. This one is selective serotonin norepinephrine reuptake inhibitor. What it does actually, you see that most of the people, when they take the SSRIs, they start feeling like groggy, tired. Some people, they say, I get like a vegetable. So, and that's due to the too much serotonin that is going to actually make you sleepy. So we need a little bit of the kick. This is the energy right here, norepinephrine. So the example of the medication that have this type of actually norepinephrine in there is going to be Cymbalta. Cymbalta is one of those medications that actually has this kick. That's why the Cymbalta, sometimes it works better on the people, and the people, they can do their daily job easier and the daily task easier because of these norepinephrine. And then we have the another what I call it reaction that it happens on the norepinephrine, and we actually get the epinephrine. That means N-methyltransferase. If you look at it over here, phenylethanol amine N-methyltransferase. So what happens, if you look at over here, forget about this part, just listen to this. Methyl, that means the methyl group right here, it's been added to where? To the amine. Okay? And if you look at it over here, ethanol, that means it's like alcoholic properties, and the alcohol always there has like a OH, you know that in their group. So what happens, we're adding actually, we are transferring basically and methyl right over here, and we're going to get the epinephrine. You see how these actually structure are so close? And epinephrine, it's very important at the moment of the fight or flight, when your body actually start having like when you see, for example, a scene that kind of scary and you want to escape from the place, what happened in your body, the vasoconstriction is going to happen basically due to the epinephrine, and also the palpitation of the heart is going to go up when the epinephrine is there. And then we see that the sympathetic nervous system is going to get actually stimulated. And when that system is actually stimulated, it's going to put you in a fight or flight, and you start actually fleeing from the place. So epinephrine also is very important chemical in actually medicine. And you know that we have like a EpiPen. When you're using the EpiPen for the people that have an allergy, it's going to actually help the people when they get like a severe allergy things. They use the EpiPen due to the epinephrine, because epinephrine is going to help with the what I call it, severe allergic reactions. And this is the ingredient of EpiPen that I use it as emergency for the people with the high allergy. All right, guys, thank you very much. I really appreciate for watching my videos, and I see you in the next video. Thank you.